long was it going for? 40 seconds? Okay. Okay, so last time we picked up on we were starting the continuous time Fourier transform, and I was starting to talk about the delta function. There's a couple things I want to go over. So I emailed out the information on how to access the lectures from the web, and I think that in order to get access to the lectures, you either have to be a engineering professional education student, or you have to be on campus. So, and that means, I said in my email that you could VPN in, but I'm told that that doesn't work. So if there's some reason, there was at least one case of a student who just simply couldn't get onto campus. They were stuck in another country. So I emailed, and the engineering professional engineer, whatever it's called, the continuing education people, they were able to set it up so I think that person can direct access. So contact me if you have a problem. And let me see. Let me see if there was any other issues. Oh, I know, there was one other thing. So I did something a little sneaky that you're not going to like, but I did it anyway, okay? So I added a laboratory, okay? So the first laboratory is due at the end of next week, okay? Okay, so I thought that wasn't unreasonable because you have 2 weeks for the first laboratory. And the first laboratory, there's some things in the first laboratory which involve, like, I think printing the image and things like that. You can interpret those components, like, loosely, okay? The main point is, filter the image and so forth, okay? Because I know that some of the interpretation of those commands doesn't make complete sense in the context of emailing your file as an electronic solution as an electronic version, okay? But the main thing is you need to implement the filters and so forth, which hopefully isn't too bad. There's templates for the C program, so you might want to get started on that as soon as possible. So if you have questions, you can come and ask. And yeah, because there's going to be a third lab which isn't yet posted, which I want to do some stuff on eigensignal analysis, because I think it's a technique which is pretty broadly used these days, and just introducing you to it and thinking about it. And so we're going to hopefully we'll have a first draft of that lab. That lab might have a few little bugs in it, because usually what happens is the first time we do one of these, there's some little problems and so forth, but hopefully it'll be close. Okay? All right, I don't think there are any. Are there any other questions? Okay. Okay. So we're talking about the continuous time Fourier transform, and I wanted to talk about the delta function. The delta function actually isn't a function. Oh, I was using the computer. Maybe I'll log into it again, because that seemed to work out pretty well. It looked fairly good. Okay, I'll let that start. But I also want to be able to write on the pad here, so I think I'll use a combination. But so a delta function is actually not a function, and the reason is that the way that intuitively a delta function is supposed to be formed by you have a say like a square pulse, and the width of the pulse is epsilon, and the height of the pulse is 1 over epsilon. So the area is equal to 1, right? And then what you do is you sort of take the limit as epsilon goes to 0. Unfortunately, that's an intuitive explanation of what a delta function is, but it doesn't mathematically work, because if you take the limit, so call this thing here delta epsilon of t. If you take the limit as epsilon goes to 0 of delta epsilon of t, that's equal almost everywhere to 0. except for at 0 where it's equal to infinity. But at 0, the fact that it's the value of a function at any one point, well, first of all, infinity isn't even a legitimate value, so it's basically just undefined at 0. And then, so any function any function's integral is, okay, the integral of any function is invariant to its value at a finite number of points. So if you just you take any function, you change its value at a finite number of points, its integral is the same. In fact, it's worse than that. It can be a countable number of points, and its integral is the same. So basically, if you take this thing here, so basically what happens is that the integral from, say, minus infinity to infinity of the limit as epsilon goes to 0 of delta epsilon of t dt, that's equal to, that integral is equal to 0. And, but if you take the limit as epsilon goes to 0 of the integral from minus infinity to infinity of delta epsilon of t dt, well, this thing is always 1. So the limit as as epsilon goes to 0 of 1 is just 1. So that's just 1. So these are not equal. So you can't exchange the limit and the integral in this case. So therefore, the delta function is not a function. Well, okay, so how do I go from that? Okay, so if the delta function were a function, then the delta function would have to be this. And that function doesn't have the properties you associate with a delta function, which is this. The delta function is supposed to have the property that its integral is equal to 1. So you're basically caught between a rock and a hard place. There's no consistent definition of the function called the delta function. So consequently, the delta function is not a function. It's, in fact, sometimes they're called distributions, but it's really an operator. So it's shorthand notation. The delta function by itself has no formally well-defined meaning, okay? But if you take it and you multiply it by some other function and you integrate that, that's equal to this function evaluated at 0. Assuming that g is continuous and integrable. If it's because you could change g's value at like a single point and cause problems. But so this is really the definition. So, but you can think of a delta function in this way, that it's an impulse. It's what happens. It's the limit as a force becomes, say, the typical examples, you have billiard balls. And does everybody know what billiard balls are? Oh boy, yeah. They still, yeah, okay. It hasn't disappeared culturally yet. Okay, so when they touch each other, you sort of get an infinite force for an infinitely short period of time. An infinitesimal, but the total momentum shift is the integral of the force over time. So it's, so that's sort of the logic behind a delta function. Okay, but it's nice to keep in mind that it's not truly a function, because every once in a while, if you start believing in this stuff too much, you'll get the wrong answer, because you have to be careful. Okay. Enough said about that. Okay, so good. This is just saying this. Okay, now you can compute the Fourier transform of all these standard functions. So the Fourier transform of a delta function is 1. So that means an impulse has all frequencies and 0 phase, assuming that the impulse occurs at time 0. And there's a duality property of the continuous time Fourier transform, which is that the formulas for the Fourier transform and its inverse are very closely related. So let me just go back and look at this. So the formula for the Fourier transform and the formula for its inverse look almost the same. The only thing that's different is this minus sign in the integral. But so basically, if you know the Fourier transform of something, then if you treated that something as a Fourier transform itself, then the inverse Fourier transform kind of, well, okay, there's this duality property. The Fourier transform and its inverse, the operators look essentially equivalent except for a time reversal. So because of the duality property, we're going to see that if you know the Fourier transform of something, you can switch the role of the transform and the signal and the time. You can switch the role of frequency and time, and you basically have another Fourier transform pair, except for the fact that there's going to be a time reversal. In this case, the signals are symmetric in time anyway, so the time reversal doesn't matter. So the Fourier transform of 1 is a delta. So intuitively, if you're an electrical engineer, we talk about signals, and the classic signal was the signal that you got that comes in the wall socket. Okay, okay. So you plug your lamp into the wall. Okay, and there's a 60 hertz signal there, right? So sometimes this is called the value a constant. If you have a signal which is in time, so this is time. If it's constant, right, then it only contains one frequency. The one frequency it contains is the frequency at 0. So this is F. So you have an impulse at 0, right? And if you have an impulse in time, it contains all frequencies. So this is F. So it looks like this. So the Fourier transform of a constant is an impulse, and the Fourier transform of an impulse is a constant. And this is sometimes called DC, or sometimes I call it DC because I'm an electrical engineer. And DC stands for direct current, which clearly has absolutely nothing to do with any of this, except for, all this kind of grew out of having Thomas Edison and what's his name, the fellow who's in our, bronze bust is in the atrium of the MSE building. Tesla, and all those fellows figured out how to generate power and distribute it so that we all would be able to plug our computers in and turn on the light bulbs. So this is direct current. Okay. Now, okay. So now, so here are continuous time Fourier transform has a variety of properties which are very important, and I'm assuming you already know them. So there's the Fourier transform is linear. Since its formula for the Fourier transform is the integral is linear, so the Fourier transform inherits that linearity, which is to say if you take the Fourier transform of the sum of two signals, it's the sum of the Fourier transforms. So the transform of the sum is the sum of the transforms. And conjugation in time, now, usually the signals we'll deal with are real valued, but if they're complex valued, then conjugation of the time signal corresponds to taking the conjugate and frequency, reversing it in frequency. Now, if the signal's value is real, we're going to find what this means is, okay, if the signal's value is real, then the conjugate of a real valued signal is the original signal, right? Conjugation of a real value does nothing, okay? By the way, just to recall, when you conjugate something, you take the negative of its imaginary part, and the real part stays constant, right? So in that case, this can't change, right? So what this tells you is that it tells you that if f of t is real, then what it tells you is that f star of minus f must be equal to f of f. Okay? So that means that the Fourier transform of a real valued signal is conjugate symmetric. So that means that the magnitude of f of minus f equals the magnitude of f, and the phase of f minus f equals the negative phase of f of f. So if you do a phase and magnitude plot, again, it's going to be clear that I'm an electrical engineer, because Electrical engineers love to do this. What they do, you take amplifiers and you look at the frequency response, and the amplitude of the frequency response does something like this, say. And if you look at the phase, it does something like this. So it's got to be conjugate symmetric, the phase, and the amplitude has to be symmetric. And notice that the derivative of the phase is always negative. For a real system that's causal, a causal system has the property that you can't get an output out before you put the input in. Okay? If for a physical system that's causal, the phase has to be has to have a negative derivative, because otherwise what you could do is put a narrowband signal into this one region here, and you could get the narrowband signal out of the system before it went in. You could put a narrowband pulse in, and the narrowband pulse would come out before you put it in. So that would be a problem for a causal system. So as an electrical engineer, I naturally draw these things this way. So this is the F of F, and this is like that, okay? Now, wow, so we just covered an entire semester of undergraduate electrical engineering. That was really fast, okay? So moving right along, now we're going to move on to the continuous space Fourier transform. So the continuous space Fourier transform is much like the continuous time Fourier transform, except for now it's a two-dimensional signal, so we have x and y. And u and v are the corresponding frequency variables that correspond to x and y. So u corresponds to x and v corresponds to y. And now it turns out that, and then this is the inverse. Now, so in this expression here, maybe we could zoom in just a little bit on this. Okay, that's great. So it turns out here that notice x multiplies by u and v multiplies y. So it's like an inner product between the uv vector and the xy vector. And so it all works out quite nicely. We'll talk about this a lot more. But we're going to see that the Fourier transform, the continuous space Fourier transform, is what you can call a separable transform, because you can really take the continuous time Fourier transform along one variable and then take the continuous time transform along the other variable, and you'll get the continuous space Fourier transform. So, and moreover, it doesn't matter which order you do that in. So if you take the continuous this continuous time Fourier transform along the rows and then the columns, or the columns and then the rows, you get the same result. So those two operators commute. Okay, there's some practical realities. Okay, so first of all, okay, x. So there's sort of an ongoing point of confusion that's going to be throughout the class, and I apologize for it, but I don't think there's much I can do about it. Which is that the standards, the conventions for the variables, there's like 3 different standards of conventions for variables that collide in this class. Okay, and I don't know how to avoid the collision because I can't change either of the 3 fields, which are well established. Okay, so one standard is this. You know, since junior high math, that x goes this way and y goes that way, right? Okay, but unfortunately, that's not what people in image processing do. Okay, because what happened is that in, I don't know, the 1940s, they invented TV. Okay, so this is TV. It looked kind of like this. Okay, and when they invented TV, they did it so what they had to do is draw on the surface here. So they had this, and it has to be a 1D signal, and it's analog, so it went like this across the top, and then it went like this. And it's very likely that the reason they did that, I'm guessing really here, but I'm going to really go out on a limb and say it's because this was mostly invented, to my knowledge, in Sarnoff Labs, okay, which was part of RCA. NBC actually was a part of RCA, which was the Radio Corporation of America, and then later it was sold to General Electric. Okay, so actually NBC still is owned by General Electric, but Sarnoff was sort of the Bill Gates of the time. And there was a guy who, of course, the actual technical inspiration and inventor, his name has been more or less lost in history because Sarnoff was the sort of financial mogul, you know. But the technical brains in the operation was a guy named Armstrong, who I'm sad to say, and I think this is correct, we should double check this on the all authoritative Google, committed suicide by jumping off of a building, I think, but maybe that part's wrong. Okay, you better double check all this stuff, okay? But this guy, Armstrong, was quite impressive because he did some very amazing things. He invented FM, and he really sort of basically invented the standards for modulation that are used in FM radio today. And then he also used those methods to design the, basically, either played a major role in developing the standards for NTSC TV, which is still used today, amazingly enough. I mean, it's really been quite a while, right? 40, 60, almost 70 years, right? So it's pretty impressive, okay? But anyway, it didn't end altogether well. But, okay, so this guy obviously read in English, okay? And English goes from left to right and top to bottom. So, you know, I guess this is probably why he did it this way, or, you know, or his graduate student did it this way, who also got no credit at all, okay? Okay, anyway, so, okay, so for that reason, in imaging, the axes go like this, because you go x to y, this is sort of the fast variable, and this is the slow variable, right? But then to confuse matters even further, if you have a matrix, usually matrices, if you have a matrix, this is A of Mn, right? So M is usually the row index, and N is usually the column index, right? So it's kind of a mess. What can I tell you? I mean, so you should be aware of this, because all three of these standards are strongly are widely adopted, okay? So they're not going to change, and they kind of clash a bit when you go to do imaging. So you have to be a little careful. But, okay, so we'll mostly use this, okay? So, so what ends up happening is you have a picture here, okay? And this is X, and this is Y, right? And what will happen is that if you have like horizontal bars like that, or vertical bars like that. So unfortunately, I don't think I wore. Oh, I did. Well, no, I wore a checkered shirt. So I often try to remember to wear a striped shirt for this lecture. So you can see that those are vertical bars. Those have high frequencies. So this would be U, and I guess we could draw V down this way just to keep things consistent. So that would have high frequencies here and here, right? And if you have, this is X and this is Y. If you have this is V, this is U, okay? Here and here, those would be the high frequencies you get there and there, right? So horizontal bars like this correspond to high frequencies in V, and vertical bars correspond to high frequencies in U. And as you might expect, then if you have this is X and this is Y, if you have diagonal bars, that corresponds to high frequencies along the diagonal direction. So the Fourier transform is rotationally invariant. If it weren't, that would be pretty disturbing. So if I take the Fourier transform or something, if I rotate the image, then the Fourier transform needs to also rotate. It makes sense. I mean, it's not obvious by just looking at this formula that it should be rotationally invariant, but it is. And we're going to prove that in just a moment. Or maybe you're going to do it as a homework. But I'm going to state it formally in just a moment, and then I'll leave the proof to you. But it is invariant to rotations. Now, that's the continuous space Fourier transform. When we get into the discrete case, and I don't want to jump ahead too far because I'll confuse you, but in the discrete Fourier transform, so if we're talking about sampling, and implicitly I'm talking about sampling if I'm talking about like digital TV, because then you have a sampled array in 2 dimensions. Then rotational invariance is an entirely different matter, because in fact you can't really even rotate it, because if you do a rotation by some arbitrary amount, the points don't fall on the grid anymore, so you've got a problem, okay? But in a continuous space, rotation can be done with impunity, and it rotates the Fourier transform. And okay, yeah, that's pretty much it. There's a lot of other related issues, but we'll leave them for later. Okay, good. Now there's a set of functions which are useful in 2 dimensions, just like in 1 dimension there's a set of functions, and some of them are listed here. So you can have a 2-dimensional delta function, which is the product of 2 1-dimensional delta functions. So this is like an impulse. Instead of its area being 1, the volume of this is 1. And you can do the same thing with a rect or a sinc. Now, there's other thing called a circ. I'm going to talk about this in just a minute. So the circ is okay, for the rect function, it looks like this, where that's 1 on the inside and 0 outside. So that's not rotationally invariant. If I wrote that clearly, it looks different at different rotation angles. But so there's more than one way to generalize the concept of a rect in 1D. So the other way to do it is to use a circular function like that. And that's what this is. By the way, the rect function has unit area. Its amplitude is 1, so the cutoff here is 1/2 and minus 1/2. So in this case, that point right there is 1/2. All right. Does that make sense? Okay. So a function separable if you can represent the function as the product of 2 functions in each of the 2 dimensions. So f of x, if f of xy can be written as g of x times h of y, then we say it's separable. So are these functions all separable? Don't look at the answer. So is this separable? Is that separable? Is that separable? Is that separable? No. I mean, it might be that if you manipulated it, it would be separable, but it doesn't work out that way. So you can't write that as you can't write that in this form. So not all useful functions are separable, but some useful functions are separable, right? Yeah, so this is going to come up later because it's very important in some properties of the 2D Fourier transform. So some of the 2D Fourier, the continuous space Fourier transforms properties are directly result from, they're direct extensions of the continuous time Fourier transform. So they're sort of the obvious thing to do, okay? And I listed them on this page. So linearity is pretty much the same, and conjugation is pretty much the same. The only thing you have to be careful about here is that you have to reverse in both u and v, and that's going to come up later. So here's an interesting point. So if you have the continuous space Fourier transform, okay, so let f of x, y be real. So if f of xy is real, then we know that f star of u v must equal to, oh, I'll put the minus sign here. It doesn't really matter. Okay, f star of minus u minus v is f of u v, right? So, that means, well, I mean, that basically just means that the Fourier transform is conjugate symmetric. So it means that if I take, that's equivalent to saying that f star of uv is equal to, well, I guess I'm not sure it has any deeper meaning. F of u minus uv, okay? So taking the conjugate is, if I, how do I explain this? If I take this point right here, right, and that's f of uv, right, then this point here, which is f of minus u minus v, is going to be equal to f star of uv. So that point there is, that point there is the conjugate of that point there. But what's not true, and what students often think is true, they get trapped accidentally, is it's not true that f star of u of okay, let me write it this way. F of minus u v is equal to f star of uv. In other words, if you just take the mirror image along one axis, it's not conjugate symmetric. So for instance, over here, this is u and that's v. So if I take some value there, that value there is not the conjugate of that value. So I put a not sign there. It's not true. Those are not equal. So flipping along a single axis does not conjugate the signal. It's not symmetric. The magnitude is not symmetric across one axis for a real valued signal. So a lot of the signals we deal with will be like images, so they'll be real valued. So, but that doesn't give you symmetry this way, and it doesn't give you symmetry this way. But it does give you symmetry through the origin. So you have to flip it twice, this way and then this way. Yeah.
What's the difference between this row and the one that
This one and this one?
Yeah.
Because here I have minus u, but I don't have minus v.
Same thing as the other.
Oops. Thanks for pointing that out. So this is true. This is false. I almost exactly taught you the wrong thing. Okay, is everybody clear on that? Because it's a really, you might say right now, oh, well, sure, he's obvious, right? But it's the kind of mistake that is very easy to make in practice. You just start to automatically think that this signal must be symmetric this way, and it's not, okay? You think it's symmetric this way because you think, oh, well, for 1D, in the 1D case over here, right, that the magnitude signal was symmetric for the real value case. But in 2D, it's not. Okay? Now, it actually is symmetric along the u-axis, but once you go off the u-axis, it's not necessarily symmetric. All right? So it's good to point out pitfalls, places where you can get confused and make errors. Okay. Okay, so now, I skipped something on the continuous time Fourier transform, I think, and also, so I almost skipped it again on the continuous space Fourier transform. So there's a Parseval's theorem, and the more general statement of it is the inner product property. So you can calculate the inner product in space is equivalent to inner product in the transform domain. And and there's not even a constant in there, is there? That seems a little suspicious to me. Is there a constant? Let me double check that. Yeah, there's no constant in there. So So if I make F and G equal, then then F times F star is just the magnitude of F squared. So the energy in time or space is equal to the energy in frequency. So that's just a result of the fact that the Fourier transform is an orthonormal transform, right? So energy is like length, okay? It's actually like length squared, right? Because if you calculate the length of something, you calculate, so length here is equal to the sum from, say, n equals 1 to n, right, of x of n squared square root. That's the length in an n-dimensional space, right? So energy is equal to the sum from n equals 1 to n of x of n squared, right? So this is equal to length squared, right? So if you have an orthonormal transform, so this pen is a vector, right? So let's say that pen is a vector. Now you're only seeing a 2D version of this vector, but okay. Well, what can I tell you? So if I move this vector around in 3 dimensions, that's an orthonormal rotation, right? Because it's orthogonal. Now it's hard to imagine. You're not totally visualizing, because it's only a single vector. You're not totally visualizing the fact that it's orthogonal, because you basically, what I need is like a ball, okay? Imagine I have a ball, okay? This is a ball, okay? So the ball rotates, right? It's a rigid body rotation, right? Now, if it's an orthonormal transform with a positive determinant, then this is like this. And if it's got a negative determinant, then you'd have to like reflect it through a mirror, okay? Okay, so if the determinant's positive, then it's just a rigid body rotation in 3 dimensions, right? And in particular, if I had a vector in there, then the vector would just move, right? So if I do any rigid body rotation in 3 dimensions, lengths are the same. And since lengths are the same, energy must be the same. So the energy computed in frequency or time or space has got to be the same. That's all Parsifal's theorem is saying. It's just saying it's a rigid body rotation because it's an orthonormal transform. So, and the proof is basically equivalent. Okay. Now, one thing that happens that's kind of interesting is this. There was one of my favorite properties of the Fourier transform I skimmed over. I have to go back and redo it. Okay. So, my favorite property of the Fourier transform is, drum roll please, okay, can anybody guess? It's the scaling property. Okay. It should have been obvious. Now you'll know. That's going to be on the exam. Okay? One of the exam questions is going to be, what is Professor Bouman's favorite property of the Fourier transform? Okay, so if you scale something, okay, what happens? So if you have a signal like this, okay, and you stretch it out, so then it gets longer. So this would be A equals 1, and say this is A equals 1/2. Because if A is equal to 1/2, it's going to be stretched by a factor of 2. Because the value t has to be twice as large to produce the same output. Okay? So when you take the Fourier transform of that, so if you have a signal in time, right, and you stretch it out, what happens to the frequencies? The easy way to do this is just to imagine, okay, so actually, so you see, you're all too young to know about vinyl phonograph albums, right? Vinyl albums, LPs, long playing, okay? So they look like this. And then there's a little thing on the end, okay? And there's a needle that goes into a little groove, and the whole thing rotates, okay? And it goes this way, actually. I had to think about that for a moment because it's been a while. Okay, now, okay. So back when the Beatles were popular and things like this is how you got your music. Either this, the long playing, or the 45, okay? So now, when this thing produces a signal, right, if you slow the rotation of this thing down, then what happens? The signal gets stretched out, right? Now, if you slow this thing down, what's going to happen to the frequencies? Are they going to go up, or are they going to go down? They're going to go down, right? So the frequencies will go down if you stretch the signal out. And if you speed the signal up, it's going to go, the frequencies are going to, it's going to go up, right? So it's going to go, right. Don't make me embarrass myself too much here, okay? Go with this, okay? So, now what's going to happen is that, if you stretch the signal out, okay, the frequencies go down. If you push the frequency, if you compress the signal, the frequencies go up. So compression in one domain is expansion in the other. If you really learn this well, you will have acquired a very valuable piece of knowledge which will distinguish you in the workplace. Because most people never really understand this, okay? There's a few basic things that signal processors understand that a lot of other people don't understand. They don't understand this, and they don't understand the sampling theorem, okay? So, because it's actually pretty counterintuitive that as you squeeze things together, so we'll see that in discrete time, when we take a larger window, we get finer sampling in frequency. So stretching in time tends to compress in frequency. Compressing in time stretches in frequency. The other thing that's interesting about the scaling property is that it has no direct analog in discrete time. So when you go to, so I'm sort of jumping ahead here, but if you sample a signal, and you stretch it, when you stretch it, the samples don't fall in the right spots anymore, right? So when you stretch it, you've got a problem. It's like, have you ever played the game of musical chairs, where you have like n plus 1 people, but you only have n chairs, and they play music, and you walk around, and then when the music stops, you have to sit down. So there's one person who doesn't get a chair, right? So the same thing happens when you have the samples and you squeeze them. They don't fall on the right grid points, and some sample doesn't have any place to go, okay? So what happens is that this all works, the scaling property works beautifully in continuous time, but it doesn't work in discrete time. And it's actually a wonderful thing that it doesn't work, because the fact that it doesn't work in discrete time has employed thousands and thousands of engineers for decades, okay, trying to solve this problem. So there's multi-rate filtering, and there's wavelets, and there's all kinds of fancy mathematical techniques have been used to address this fundamental problem. That what do you do when you have to resample a discrete time signal? And which brings me to my next point, which is that in the analog of the scaling property in 2D is really rotation. Because rotation is sort of a more general thing. You could stretch, and you can compress, and you can also rotate, okay? And rotation in 2D works very nicely in continuous space, but in discrete space you have problems, because the points don't fall on a grid anymore. So the two distinguished properties, in my view, for continuous space Fourier transform are separability, which has no direct analog in 1D, and a separability says that if a signal is separable in space, then you can compute a continuous space Fourier transform by computing the continuous time Fourier transform of each of the two corresponding signals, f and g. So you compute the continuous time Fourier transform of f and the continuous time transform of g. You multiply them together, and that's the continuous space Fourier transform of the 2D signal. In rotation, we have this property, which is that if you apply a general linear transform with that's invertible, A, so its determinant is not 0, then the Fourier transform of this expression is given by this, okay? So we'll talk about this more. If A is an orthonormal rotation, then we'll get the fact that that a rotation of f corresponds to a rotation of its transform. And proving this result is relatively straightforward. You should be able to do it, actually. That would be like a perfectly legitimate exam question, because you basically just kind of grind through the formulas and do some substitution of variables and so forth, and you should be able to get that the Fourier transform of this has this form. Okay, it's a good problem to solve. Yeah. Yeah, A is a matrix. So here, A has 4 values in it, and this is x, y, right? So this is A11, A12, A21, and A22, and it's not necessarily a symmetric matrix. And but the only thing we're assuming is its determinant isn't 0, so that it's invertible. Mm-hmm. Okay, now the continuous space Fourier transform. The continuous space Fourier transform it's a separable transform. I mentioned that before. And what I mean by that is that you can compute the continuous space Fourier transform by first taking a continuous time Fourier transform along, say, the x variable, and then taking the resulting function of a y and taking the continuous time Fourier transform along the y variable. Or you could do it in the other order. And it's a direct result of the fact that it's a beautiful thing that e to the a plus b is equal to e to the a times e to the b. Right? It's a very powerful concept. So, define the continuous time Fourier transform of f of xy in the variable x. Okay, so here f tilde here is now the Fourier transform of f along only the x variable. And that's distinct from the Fourier transform only along the y variable. So you basically have this. You have f of xy, and you have the first box, which is discrete time Fourier transform along x, and then you have discrete time Fourier transform along y, and that produces f of uv. So that's equivalent to the 2D Fourier transform. And that's also equivalent to, you can commute these. And this is, all right? So that's an interesting thing, because in general, linear transformations don't commute, right? So if you take, I think I'm running out of time, but if you take two matrices in general don't commute, but these operations do. Okay, I think so. Next time, are we running out? Yeah, we're running out of time. So next time we'll continue with the continuous space Fourier transform, and don't forget to get started on the lab that's going to be due at the end of next week on Friday. Okay? All right. Thanks a lot, and it's good seeing you again. Bye.